We are continuing the discussion on overview of experimental stress analysis, and in the last class we had particularly seen what is the physical principle behind some of the experimental techniques. First we saw the method of strain gauges, and I said stresses alter the resistance of the conductor, and this was a physical principle used in strain gauges. It is desirable. However, we also found temperature also alters the resistance information. So, this is a nuisance. So, you have to be very careful in strain gauge instrumentation to delineate the resistance changes due to strain and that due to temperature. So, when we see the experimental technique, we see both. We look at what is the physical principle behind it and what is the limitation, where does the limitation come from. When we go to photoelasticity, we said that we get whole field information, whereas strain gauge gives a point by point information. The photoelasticity requires normal incidence. Normal incidence is a key point. If you have a curved models, then you have to immerse it in a liquid which has the same refractive index. Then we had a detailed discussion on Moire, and Moire you are able to get the displacement. I said Moire is a nuisance in some applications. For example, in color printing you do not want to have Moire effects. And secondly, when we all come for this televised lecture, we are advised to wear only plain shirts. You can watch in some of the TV programs, if they come with striped shirts, you will have a sort of color banding, because you have a electronic camera which scans the image and that interferes with the frequency of your stripes, and you will see a color banding effect. And like I said, friction is needed in some application, friction is not needed in some application. So, Moire is not needed in color printing, Moire is not needed in televised information where you want to take care. Maybe with high definition television some of these effects are fairly addressed. But what you will have to understand is, for every technique you will have certain kind of limitation. And in Moire what we also saw was, I have a grating and which I had shown, and what you will have to notice it, when I have this grating, I make a rigid body translation and rigid body rotation. I see fringes, we get excited to see fringes, but you should implicitly understand this is a nuisance in Moire, because Moire I would like to find out what is the effect of stresses or strains introduced in the material, not rigid body rotation and rigid body translation. So, you will have to be very careful while performing Moire that you take care of the effect of rigid body translation and rotation. It is very important, it is very subtle, and we will again go back and look at, because Moire is a very interesting technique. We will look at, we started Moire by introducing the application of grids in metal forming operations, and what we saw was, we had a billet which is put with a grid, and when you have very high plastic deformation, you see these grids visually distorted, and this gives you an information on what is the level of strain introduced and how the material has flowed and so on and so forth. And what we saw was, instead of just using a grid, people also had another approach wherein along with the grid, inside the grid they had put a circle, and when you stretch the member, the circle deforms into an ellipse. So, you also get the stretch direction. And later on what we did was, instead of using only one grid, we have used two grids. We call one as a master grating and another as a specimen grating. And here the specimen grating is cross hatched, and master grating is horizontal lines, and I pull the material, pull the specimen. So, the specimen elongates as well as contracts because of Poisson effect. And what you see here is the actual specimen deformation is small, but you see a play of fringes. So, what we find is instead of using only one set of grids, if the specimen grid is viewed through another grid, moire fringes are seen, and these are very coarse fringes. And what we want to see is we want to have fine measurements, and you also appreciate that moire fringes has a magnifying effect to measure small deformations. Because it has a magnifying effect, by making measurement on the fringes, you are in a position to find out very fine displacements. And what you find here is the fineness of the grid spacing determines the accuracy obtainable in moire. Whatever you call it as a pitch, the finer the pitch, finer the deformation measurement that you can do. And here we have a situation, I have the specimen is with very fine cross hatched pattern, and I also have a master which is also having a cross hatched pattern. So, I get two sets of fringes, one set of fringes horizontal, one set of fringes vertical. See, you should not confuse these horizontal and vertical fringes to the grating lines. We have seen in the problem of a disc, the fringes could be curved. You could get curved fringes, but you interpret whether these fringes belong to u displacement or v displacement by looking at what was the master grating direction. The master grating direction is horizontal, then you get displacement in the vertical direction. Here the problem what we have taken is axially loaded member. Here you have uniform deformation. The fringes also become horizontal and vertical. So, do not carry the mental block that horizontal fringes means v displacement, vertical fringes means u displacement. Do not have that confusion. That confusion is possible by looking at this picture. This is a very special case. So, what we look at here is I can also get two information from one experiment, because I said in some experiments which is time varying, you may want to record more than one information. Recording both the information simultaneously is better, but simultaneous recording is not always good. So, you would like to have information obtained separately, and I also said that in moire it is possible to identify the displacements easily. We will see that in a few slides later. Now, we also looked at the reduction of grid line spacing was a challenge, and many scientists have contributed to it, and we have also seen as the grating density is increased, what you find was the fringes become finer and finer. And I said a thumb rule which says up to 40 lines per millimeter, you can call it as geometric moire. Even this 40 lines per millimeter is fairly small, and you are able to get a displacement resolution of 25 micrometers. And moire gives you only displacement, and from moire data strain has to be obtained by numerical differentiation, and we have seen that numerical differentiation is erroneous. So, unless you have very fine information, it is not worth doing the numerical differentiation. And we have also looked at efforts have been aimed at increasing the density of the gratings, and I posed a problem. I want to measure 1% of strain, and here it is clearly shown as 10,000 micro strain. Obviously, it is a very large value. Even when you want to measure very large strain, what you find here is you require 100 lines per millimeter. So, from 40 lines per millimeter, if you go to 100 lines per millimeter, which is very fine from pitch point of view, from pitch point of view it is very fine, but what you find here is the strain value is still very high. So, what you need to understand is Moiré is applicable for large strain problems comfortably. Okay. And we have also looked at what is the level of grating pitch that they could reduce. People have gone up to 2400 lines per millimeter. And what you find here? If you have 2400 lines per millimeter, the displacement accuracy is of the order of 0.417 micrometer, and suppose you find that you are able to see a Moiré fringe at a spacing of 1 millimeter, it is a reasonable assumption. The strain sensitivity is only 417 micro strain. It is still large, because I said we live much below 2000 micro strain for most of our practical requirements, and we may operate around 500 micro strain for many of our strategically important components. So, if Moiré sensitivity it cannot go below that, so measurement in those regions you have to look for other techniques, and we have already seen strain gauges you are able to measure up to 1 micro strain. Now, even 0.5 micro strain reliable measurement is possible. So, when you go for very fine small strain measurement, strain gauge is good, but it is a point by point information. The advantage of Moiré is I get a whole field information, and what we have seen is I also see the fringes in real time, and I also find that rigid body rotation and translation you have to be careful about in Moiré. And I said that once you take any technique you have several variants exist. So, in geometric Moiré you have shadow Moiré, you have reflection Moiré, you have projection Moiré, which cater to different field problems. And geometric Moiré is useful in plane as well as out of plane displacement, and also slope in bending of plates. And we have already seen that reflection Moiré was used to find out the curvature, and you could find out of plane displacement by shadow Moiré, and geometric Moiré can give in plane displacement. And the method of putting the specimen grating is slightly different in shadow Moiré, reflection Moiré and projection Moiré, etc. And we have also seen that Moiré interferometry is to improve the accuracy. And what you find here is primarily it is applicable for in plane displacements of planar surfaces. This is a very key point. If you have curved surfaces, whether it is photoelasticity or Moiré or any other experimental technique will have problem. So, we are happy from simple geometry to complex shapes, but once you come to complex shapes, if it is curved, then you will get information, but interpretation becomes difficult. And the greatest advantage of Moiré interferometry is whatever the equations that you have developed for geometric Moiré equally applicable, and here you have to have a specimen grating always needs to be bonded to the specimen, which is not the case in geometric Moiré. I can project the grating on the specimen, I can look at the shadow of the grating on the specimen and then do the interferometry. But once you come to Moiré interferometry, I will have to have the specimen grating firmly bonded to the specimen, and there are many techniques that have been developed. Newer materials have contributed to the improvement, and many techniques, and these are all very fine grid lines. See, the fineness makes the process delicate. And I have also identified that Moiré interferometry has played a key role in understanding the thermal stresses introduced in electronic packages and also the displacement fields in composite laminates, because composites are becoming very important for structural applications, and because of their material anisotropy, analytical modeling is extremely tedious, and at least you get surface information by using techniques like Moiré interferometry. So, what is important here is each technique has a particular domain where it has served its purpose fully. The moment you think of Moiré interferometry, electronic packaging you cannot forget, they go together. Very interesting problems in electronic packaging have been solved by Moiré interferometry. And the other concept which I wanted to say was that you are able to get the displacement information comfortably separated in Moiré analysis. And purposely this is taken like this: I have a specimen with a crossed grating, but I view this specimen with a horizontal grating. So, what is the displacement I get? We have already seen, once you have horizontal grating, what is the displacement you get? You get the displacement perpendicular to that. So, the fringes what you have here show the V displacement, and what I want is, suppose I want to see U displacement, I will change my grating, I will change my master grating to have vertical lines. So, I will have a U displacement. So, what I have is, on the specimen I bond only one grating which has a crossed lines, but I view this with a horizontal grating or a vertical grating. So, I can comfortably switch over from U displacement to V displacement. Data interpretation is not difficult. It is a very key important, because the next technique we are going to take it up is holography. In holography you will get displacement vector, it will give you U, V as well as W bundled together. Separation becomes difficult, and in the case of Moiré, by choosing the master grating appropriately, I can look at U displacement separately, I can look at V displacement separately. And all these contours, when you look at, they all have special names. We have seen in photoelasticity isochromatics, we have seen isoclinics, and in Moiré these contours are called as isothetics. U displacement isothetics, V displacement isothetics, R displacement isothetics, theta displacement isothetics, all those terminologies you will come across. So, what you find here is the determination of displacement components is simple, as specific optical arrangements are available for finding U, V and only W displacements. That is possible from geometric Moiré. Moiré interferometry gives you only U and V displacement. When you go to geometric Moiré, its variation like shadow Moiré, reflection Moiré, projection Moiré, you get out of plane displacement, you get slope, you get curvature, and each case you need to have a specific optical arrangement. Though it appears specific arrangement is a nuisance in some instances, data interpretation is lot more simpler if you have specific optical arrangement. See, what we have looked at is, we have looked at the method of strain gauges. Strain gauges is able to find out strain at a particular location. Suppose I have a known situation, I know these are all the regions of stress concentration, I can put a strain gauge and find out the strain comfortably. Suppose I have a large industrial problem and the component is so huge and you have a no clue on how to go about and find out and get started on the problem. So, in such cases brittle coating is a first step, and the name itself signifies, in this a thin coat of material that fails in a brittle fashion is sprayed onto the specimen. So, the name indicates you have a brittle coating. So, you put a thin spray of material which fails in a brittle fashion. A brittle material fails by what theory? What is the theory of failure for a brittle material? It fails by maximum stress theory or maximum strain theory, and you can call it as Morse theory, whichever way you want to call it. Okay. So, once it fails, you are able to get the principal stress direction from that. So, here what you do is you have a specimen on which you spray the material, you load the model and allow the coating to crack, very peculiar. Okay. And here the accuracy of the technique will be decided by the property of the coating. If the coating fails at a lower value of strain, lot more better, because I can even measure strains at lower levels. So, that is the principle behind it. And even the experiment is conducted in a slightly different fashion here. See, in other cases what you do is, I want to find out strain for a given load, I will go and apply that load and find out what are the contours that I got and try to interpret. On the other hand, brittle coating is done in a different fashion. What you do is, you take the model, you load it in steps, and at the end of each step I have to go and look at where all cracks have formed, go and carefully inspect it, mark them, they all carry meaning. Okay. And you see that for a pressure vessel, I have a pressure vessel here, and what we will see is, you have the pressure vessel is made of steel, that is what the grey color shows, and this slight brownish tinge, light brown, shows the area sprayed with brittle coating. Now, what I am going to do is, I am going to increase the pressure inside the pressure vessel, and what you find here is, I have first set of cracks formed. I notice that first set of cracks are formed, and I indicate the level of pressure by an arrow, and this pressure will keep on increasing. So, what I do is, I do not continuously increase the load, I increase the load to pressure P, stop the test, go to the specimen and look at the crack, and these cracks are labeled as isostatics. Not only I notice the cracks, but I also draw the boundary of the crack. So, it is connecting all the ends of the crack as a contour, and these contours are also named separately. You have those contours as isoenstatic. So, what you have here is, you apply the load, go and look at the formation of cracks, mark the boundary, then come back and increase the load. So, you will do the loading intermittently, in between you have to go inspect the cracks, and if you look at, there are many methods developed how to identify the cracks. You should not escape attention of cracks on the structure. So, you have to inspect the complete structure. There are recommendations that you should do it this in 5 minutes time, because you are having a coating, the coating should not creep. So, you maintain the load at the given pressure, go quickly mark the crack, come back and repeat the load, repeat the experiment. So, what I will do is, I will increase the load, I will increase the pressure, that is what you will see here. So, what you find is the pressure is increased, you have second set of cracks formed, and we will see this very closely now. So, what you find here is, I have increased the pressure. So, for each one of these end of cracks I note a different color, and at this stage if you are very careful, you would also see there are cracks perpendicular to the original cracks also have appeared, and I also mark a isoenstatic around them. So, the whole experiment is little different in brittle coating. What I do is, I look at the structure for a given load, incrementally raise the load in stages. After raising the load, you stop it, hold it, go and look at the cracks, identify the ends of the crack, and then repeat the next stage, and so on and so forth. That is how you do it, that is how you do the experiment. And what is important here is, this is available at a particular pressure P in this case, this is at a pressure P dash which is greater than the original P. So, at increasing pressures you get more and more contours, and if I want to find out quantitatively the information, I need to do it for two different loads and then find out the numbers. And I have also cautioned, as experimentalists people develop methodologies to extract. My recommendation for using brittle coating is to find out the principal stress direction. It is very simple. The moment you get the cracks indicate the principal stress direction. The tangent to the crack is nothing but the principal stress direction, because you have a brittle material and brittle material has failed. Why it got separated? It has reached its threshold strain and the whole thing got separated, and this naturally gives you the principal stress direction. But if you want to find out even the magnitude of the stresses developed, then you need isostatics and then do the processing, and if you really look at those equations, a very long winding. So, when you want to look at brittle coating, what you will have to look at is these isostatic patterns you have to mark it, you have to use these patterns to find out the quantitative value of stresses. On the other hand, if I combine brittle coating and strain gauges, I have a lot of advantage. The advantage what I have is, I know the principal stress direction from the isostatics. So, I can align the strain gauge appropriately on an actual test component. Normally on a free surface you require 3 strain gauges to be mounted, because you want to find out 3 components of strain tensor. If I know the principal stress direction, I can reduce 1 strain gauge per point. It is a great saving. And when you are really looking at analysis on a aircraft structure or any one of the realistic structures, you may want to handle 1000 channels, 2000 channels. So, in that you can increase the number of points by reducing number of channels per point, because each strain gauge occupies a channel. So, in large scale problem you combine strain gauges and brittle coatings appropriately, and this method is also a little different. You incrementally load the structure. At each level of the load you identify the outer boundary of the cracks, you call them as isostatic, and if you look at the equations they are mind boggling, and you also make certain approximations in the processing of the results. So, the idea is use brittle coating more for finding out the principal stress direction rather than finding out the magnitudes. So, that is what we have looked at it. The principal stress direction at a point of interest is tangential to the crack at that point. And what is the level of accuracy? The accuracy of the test is dictated by failure strain of the coating decides the minimum strain that the technique can detect. And another thing you will have to keep in mind, in all the coating techniques, what you find is, in all you will have Poisson ratio. The Poisson ratio mismatch is a nuisance in all the coating techniques, because one of the assumptions what we do is, I have a prototype and I have a coating on it, and we assume that whatever the strain of the prototype is faithfully transferred to the coating. You will have a coating with different elastic properties. The specimen will have nu s as the Poisson ratio, the coating will have nu c as the Poisson ratio. You can understand if it is stretched, you can understand you are applying the load and then both the coating and the specimens stretch uniformly. On the transverse direction, Poisson ratio plays a nuisance value. So, this you will have to live with in all the coating technique in experimental mechanics. What you will finally say is, the Poisson ratio effects are minimal, it could be neglected, or you bring in a correction factor. You have to handle this very carefully. So, Poisson ratio mismatch is a nuisance. That is why he said experiment gives you information closer to truth. In some cases you will also have to swallow a few minor issues which we are not in a position to solve. And what is the level of strain that this can give? It is of the order of 300 to 500 micro strain, and as technology advances we are able to get coating which lower and lower strain, but it is around this region. But experimentalists have not stopped like this. Once you find that there is a limitation, they have also developed methodology where they use refrigeration to reveal regions where you have strains below and develop the cracks. So, if you get into the technique, there are ways to circumvent some of these issues. And another very important aspect of this is we are very much concerned about the environment, and here the whatever the material that is used for brittle coatings, you need to have protective gear. It is not healthy for humans to breathe, and not only this, the failure behavior of the coating strongly depends on the environment. Whatever is the humidity and temperature dictates how the coating is going to behave. That means the failure strain will change. If the ambient temperature changes, if the humidity changes, because you are going to apply brittle coating in the field, you are not going to apply brittle coating inside the comfort of your laboratory. Inside the comfort of the laboratory you can control everything, you can control the humidity, you can control the temperature, you can have dust free environment, but brittle coating is a very industry friendly technique. It is used in the field and it gives a very valuable information in large structures where you want to identify zones of importance for further study. That is the way you have to look at it. You have to use this technique more to identify zones of importance that needs further attention. Then you use either photoelastic coating, or you can also use brittle strain gauges and make finer measurements. Now we move on to the technique is suitable for solving large scale problem, which I have said, and it is to be used in conjunction with strain gauge, and that is the way the technique has an edge when we want to use it in real practice. Now we move on to the next technique, holography, and this is very similar to, the name is very similar to photography. But what is holography? Holography tries to provide you complete information. When you say complete information, what complete information? It tries to give you intensity and the phase information. So, we need to understand little more when we come to holography, and the phase information is recorded as interference fringes. And before we get into some of these details, we will just see lasers are used in holography. We will just look at what we do in conventional photography, and we will look at what is that we do in conventional photography. And I have the figure of photograph of Athena, Greek goddess of wisdom, because I want all engineers to be wise. Acquiring knowledge is not sufficient to be a good engineer, you need to have practical experience. Knowledge combined with practical experience constitute wisdom. Okay. So, what you see here is you have a beautiful picture of Athena, its illumination is white light. Suppose I change the light source, what happens? This figure is much better, this figure is not even nice to watch. And what you find here is you can see very clearly there are specular information, that is you see dots, red dots laying on that, and this is what happens with any laser illumination. When you illuminate anything with laser, laser is highly monochromatic and highly coherent, but you have this information available only in this fashion, and this is your positive. Okay. Now, let us look at what is a negative. When I have a positive, when I have a negative, if I look at the negative, I can make out what does this negative contain. You see intensity is recorded when you have black in the original, negativity is white. So, it allows more light and then you get that as a black in positive. So, in conventional photography you are able to clearly see that I record intensity, and then you are able to see intensity variation, and you are able to look at this is positive and then conjecture what a negative could be, or from negative you could see what is the positive I have recorded. So, this is the information I want you to recognize from conventional photography. Now, we go back and then find out what holography is all about. So, in holography what I find is I record both intensity and the phase information, and now you have to know what is phase. Okay, what is phase you need to understand. I have a deflected object here, I have a light impinges on it and it reaches the model, and I would like you to have a fairly neat sketch of this, because this gives you in nutshell an understanding of what is phase. I have shown a deformed object and I have a laser source which hits the object, the depth is different. So, when the light scattered from this reaches the screen, it reaches at different values of phase. So, the phase carries the depth information. So, in normal photography you do not record the phase information, you record only intensity. That is what we have seen, the positive and negative. The moment you come to holography, you record in addition to intensity the phase information of the reflected wavefront. So, that makes holography different. How this phase information is recorded? Its phase information is recorded based on principles of interferometry, and what we will see is we will see the ideas listed here. So, what we do in holography, it is a process of recording and reconstructing the complete optical wavefront reflected from an object. When I say complete optical wavefront, I said intensity as well as phase, and we have seen in conventional photography one records only the intense information of the wavefront. In holography, phase of the wavefront is also recorded, and phase of the wavefront is recorded by employing the principles of interferometry. Okay. So, that is a difference, and we will go back and see how does a hologram look like and then what do you see in that. I have a hologram here, and what is the important point here is, first observation is the image is not good as what I record in normal white light, but because I record the phase information, when the observation point is moved horizontally, different perspective of the object is seen. So, you are able to get the 3-dimensional effect of the recording, as if the model is in front of you, you are able to go peep what it is, you are able to see that. I will show you that in my animation. Okay, I will also magnify this, I will show you this, and this was hologram was recorded in the lab of Professor Kothiyal and Dr. Krishna Mohan at Applied Optics Lab, IIT Madras. And now I move my head, and what you see here? I see objects behind, I see this swan is behind, and you have a statue of Lord Ganesha in the front, and then I move it to the right, then you are able to see the depth information. Are you able to see the depth information? As if the objects are kept before you, by you are able to see the depth information, you are able to get different perspective. This is recorded as if you are moving the head over the region of the hologram. But from our measurement point of view, we are not looking at only 3 dimensional pictures. Our interest is to go in for deformation. In metrology application, this is useful. Are you able to see the depth information? Are you convinced that holography records depth? Okay. Now we go back and then see the other aspects of it. So what I find is, the recording medium should have a high resolution to record this information, because I am recording both the information of intensity and phase. So I need to have a high resolution to record the information, and holography is also called as lensless photography. And we have to see further what is the implication of the use of lensless photography and how it is recorded. And traditionally they were having a very high resolution, they had holographic plates, that is how they are able to record the holograms. And now we will get into how does this. So what we find here is, see, in the case of conventional photography, the holographic record of the object will have no resemblance to the original image, but only densely packed interferometric fringes. This is my interest to show, because in the case of conventional photography, you look at the negative, you are able to make out what is recorded on that. Suppose somebody gives you a hologram, you will not know what is that unless you reconstruct it. Okay, this is the fundamental difference. So what you see here is, the hologram needs to be reconstructed to view the 3 dimensional object. And for the set of Ganesha and Swan, what is kept, if you look at the hologram is like this. We will see that enlarged, and this is what I see. Do you make out anything here? You see only some funny fringes on this. So this contains information of Swan, Lord Ganesha kept at different distances, you are able to peep into it, and then you are able to see that. So by looking at the hologram with a naked eye, you cannot see the picture, you need to reconstruct it, you need an optical arrangement to do that. Okay. And that optical arrangement is shown next, and this is what you see here. And what you have here is, I have the hologram mounted, I have a play of laser which falls on this, and you will have to look at this hologram and then record the 3 dimensional depth of the hologram. So it is not like conventional photography. Conventional photography, you have a digital camera now, you take a photograph, instantly you see what you have recorded. But in holography, you will have to reconstruct the hologram and view it. But many will disagree with me, sir, we are seeing hologram day in and day out in many of our simple appliances. When I buy a cassette, I have a hologram printed on this. What is this hologram? Though it is not needed for your stress analysis or the strain displacement analysis, it is better to know, have a common knowledge on what are these holograms. Okay. So that is what we are going to look at it now. What we will look at is, that is what we have seen, reconstruct hologram gives a nice 3 dimensional view. Now what we want to see is, recording the hologram is a sensitive and involved process. Okay. It is not a, that is why it is used for security devices. However, the reconstruction is fairly simple, though for reconstruction I need an optical arrangement to do it. So, this has made holography attractive for addressing security issues, as it is difficult to copy. That is why people use hologram stickers. Though for measurement purposes one uses a laser for reconstruction, with advancements in technology it has been possible to construct holograms that could be reconstructed using white light. So, what you see as holographic stickers are nothing but white light holograms. There is some sacrifice of quality in the process, but at the same time, because holograms are difficult to make, duplication is difficult. So, you are able to give a guarantee to the genuineness of the product if you see the hologram given by the manufacturer. And these holograms are named as rainbow holograms. Why they are called as rainbow holograms? There is a reason behind it. Many times you do not know how to even look at the hologram, how to look for information, and we will see what are these rainbow holograms. And what you have here is, these are made by double holographic process. An ordinary transmission hologram is used as the object, and a second hologram is made through a slit. It is an optical requirement, and the focus here is, I want to see the reconstruction without going into complicated optics, just normal white light should be good enough. That is the purpose behind it. So, what you have here is, the slit process removes the coherence requirement or the viewing light, and hence the 3-dimensional object could be viewed with white light. So, that is the advantage. So, one of the greatest application of holography is in security, which you see it has become so commonplace. Almost anything you buy, it comes with a hologram sticker. And if you go back in history, it was in 1983 first the Visa card, the Dove hologram was used. I will just show you that. So, what you have here is, you have a Visa card Dove hologram. This is a Dove, and you could even see the color change. And what we will do is, we will look at another hologram which was also released during the same time, how to view a rainbow hologram. What is the difference between a conventional hologram and this? This is more from a point of view of appreciating how your holography is used in various applications. So, what you find here is, I have a beautiful hologram here, and we will have a magnification of this and then see the demo. And what you have here is, if I move my head horizontally, I will repeat it again, you could see beautifully the 3-dimensional depth of the eagle. Could you see that? I will repeat it again. You are able to see this, and this hologram was recorded by Haynes of ID-Tech Images. It was done in 1983, and this was published on the National Geographic Journal as a cover page. They were popularizing holograms at that time, and what you saw here as animation, it requires skillful photography to reveal and assemble them together. See, in the normal books, what they will show is, they will show one extreme view, one middle view, and one another view to show that it is recording the depth information. And this was done by Guru Prasad, who had done it at IIT Madras, and these are assembled to give you a nice 3-dimensional view, but still it does not explain why it is rainbow hologram. So, you have a horizontal slit limits the vertical perspective of the original hologram, and the rainbow hologram retains a 3-dimensional character only when the eyes are moved horizontally. When I move my eyes horizontally, I have a 3-dimensional representation. If I move the eyes vertically, I would not have a 3-dimensional representation. I would have only rainbow of colors, and here again recording is difficult. Its recording is very difficult, and that was done by my student, and that is what you will see here. You will see beautifully the play of colors. So, I have this on the vertical movement. When I do it, I have play of colors, and this is what you see. You could see the whole eagle as green. I will move further. You could see the whole eagle as red, and this is this is because of the aberrations. If the illumination is not all right, you do not see this comfortably. And so, what you see here is you are able to see different colors of the rainbow. I am able to stop only at green. I want to stop it at blue. Let me see one more. Okay, I am able to stop only at, my reflexes are such, I am able to stop only at red or blue. Okay, I will also want to stop it at blue. Okay, no, I will stop it at blue. I will try one more time. No, I am unable to do that so fast. So, what you find here is you have a nice hologram, what you have the rainbow of colors, and here because the images are not assembled properly, you say a semblance of depth, but it is not actual depth. What you saw in the earlier one, when you move the head horizontally, you saw a beautiful depth. Here you see only colors are different. Okay, that is why it is called a rainbow hologram, and these holograms are commonly formed as surface relief patterns on a plastic film, and they incorporate a reflective aluminum coating which provides the light from behind to reconstruct the image. So, what we saw in conventional holography was you need to have a laser arrangement to view the hologram. You cannot view the hologram like reading a normal negative. You need an optical arrangement to do that, but people found as advancements developed, they could do away with reconstruction optics. Normal white light can do it, but in the process your three dimensionality on both directions is lost. On one direction you are able to preserve three dimensionality, on other direction you see only a play of colors. That is interesting, that is very interesting. So, you have a play of colors, and that is a way you have to verify whether it is a genuine hologram or not. And these days they have multi-layered holograms. You will see on one layer one information, another layer another information, and this use of holography is more from security point of view, less from stress analysis point of view. So, what we will do is we will try to look at what is the use of stress analysis in the next class, and you will also have to remember holography was invented in 1948, as recent as 1948, and the person who developed holography or invented holography was given a Nobel Prize for it. So, it is a invention of that fundamental in nature that he got a Nobel Prize. It is Dennis Gaber who got the Nobel Prize in 1971, and this holography finds numerous applications, but we will focus our attention from solid mechanics point of view. How do I find out the displacement? Primarily it gives you displacement. I spend little time on rainbow holograms because that is what you have access to easily, and you should know, at least go and educate your people at home how to view an hologram. So, if you have a rainbow hologram on horizontal direction, you will have a 3-dimensional representation. On the vertical scale you will see play of colors, but now you have layered holograms. So many varieties have come, so many varieties. Even there they have used color, try to bring holography in color. There are so many developments. So, those are all like more from marketing point of view, displays, and then public use of holography for fun. We will not get into all that. We will only look at how holography can be exploited for stress analysis. That we will take it up in the next class.